Alright, so welcome back to the second segment of the first module in week 10. Let's continue from where we left off in the previous segment. So if you recall, we were looking at this recursion tree that is generated by our recursive algorithm, and we concluded that this tree has an exponential number of nodes, leading to the conclusion that the algorithm that we just wrote has an exponential time complexity, because the time complexity is proportional to the number of function calls made, and that's what is depicted in this recursion tree. That's about as far as we got last time, and what I'd asked you to do was to think about whether you can identify any redundancy of computation in this recursion tree, which will hopefully give us some way of saving some time. So one thing that you may have noticed is that there are parts of this recursion tree that look exactly the same. In particular, for instance, if you look at this function call that's being made to 4 here, that looks rather a lot like the function call that was made to 4 earlier. And the information that we are getting out of these function calls is exactly the same. So this entire computation that's highlighted in orange is completely redundant, because by this time you have already performed the exact same computations a few moments ago when you went over the function calls that have been highlighted in yellow in this picture. They're to the bottom left of your screen. So when you look at this picture, it seems like we're being rather silly in redoing a lot of work that's already been done. So the question to ask ourselves at this point is there any way that we can leverage the information that we have from computations that we have already done so that we don't have to do it again? And that's exactly the process or the strategy of memoization. So essentially, we want to remember the work that we have done before so that we don't have to do it again. So let's take a look at how this works. Essentially, we want to store the outcomes of these prior function calls so that at any point of time, whenever we have a recursive call, what we can do is really examine if there is a need to go down the recursive rabbit hole prompted by this call. The way we do this is check if the information that we would get by performing the recursive computation is already available to us. If it's already available to us, then we avoid the recursive call altogether. If it's not available to us, that means we are doing this operation, or we are doing this computation for the first time, and it's okay to actually invoke the recursion. So notice that overall your algorithm is trying to track n pieces of information, where n is the number of stones that are there in the input that you're working with. So to implement this in your program, what you would typically do is declare an array or a list or a vector of size n and use that to actually store the output of the recursive calls as you go along. So let's take a look at how this would actually pan out in your program. So here's the code again, but now it's fixed to account for memoization. And the difference between this and the recursive program that we saw earlier is so small that I wouldn't be surprised if you didn't even notice the difference from a quick glance. So let me actually highlight the line that makes all the difference. It's this conditional statement here, which is basically saying, look, if you already know the answer, then you don't have to go through the process here. Okay, so what we have done behind the scenes, in the sense that you don't see it on your screen right now, is we have initialized a memo array or a vector where all the values by default are -1. -1 in this problem is essentially a way of saying we don't know the answer yet. If you're working with a problem where the value -1 has some meaning or significance, then that's not a good value to initialize your array with. Basically, use some number which has nothing to do with your problem so that you can really use it as a code for saying, I don't know yet. So coming back to our program, here is what the code is doing for you. It's saying, okay, we want to know the answer for n. The first thing we do is check if we know this answer already. So if the array value at n is something other than -1, that means Well, that's a deja vu situation. We have already been here, we know what the answer is, and we can simply return in this case. Okay, so if it's not -1, notice that the code doesn't execute any of the recursive calls, it doesn't do any other work, it immediately returns the answer. On the other hand, if the array does report -1, that means that this is unknown territory, we don't know what's going on, and we do need to go down the recursion rabbit hole to figure out what the answer is going to be. So with this revised version of the recursive algorithm, let's take a look at what's going on in the recursion tree. So notice that all of these function calls that have been highlighted here will actually not execute in terms of recursion, but they will immediately return the answer, because at the time that these function calls happen, the same computation has already been performed before, and the memo array is actually going to report an actual answer. So all of these all of this work in the recursion tree basically does not happen and is avoided, and your recursion tree will now essentially look like a linear path. Notice that this is really the leftmost sequence of executions, and once all of those are complete, as you walk your way back up to the root of the tree, there will be function calls, but they will all return immediately. So no new recursive instances will be spawned, and the total amount of work that is being done now is actually linear. So I do hope that you find this as amazing as I do. I think a little bit of extra space and a couple of lines of code adjusted for can lead to really tremendous time savings. So that's the impact of memoization. And whenever you come up with recursive solutions, do watch out for the potential to memoize. What you really want is a situation where there is a lot of redundant work so that you can find ways of avoiding it and saving yourself some time. So we will have more to say about general principles in just a bit, but while we are at it, let's actually see how this algorithm plays out for the example that we started off with. So we have the frog here on the third stone, mainly because, as we said, for the first two stones we already know what the costs are going to be. These are the base cases. So in the first stone, let me just recap that the cost we agreed would be 0, and on the second stone the cost would simply be the absolute differences, the absolute difference between the heights of the first and the second stone, and in this example that happens to be 20. So let's actually go ahead and make a note of this in the recursion tree as well. So these are the values that are returned by these two bottommost function calls, which is where the work happens directly and there are no further calls. So these values are reported and pushed upstream to the calling function, which is trying to figure out what is the answer when there are 3 stones in the picture. So at this point, remember, we're asking ourselves, how did you end up on the third stone? There are 2 possibilities. Either you came in from the second stone and that jump would have cost you 50, or you came in from the first stone and that jump would have cost you 30. So the final answer is the better of the 2 options between 50 plus 20 and 30 plus 0. So here 30 plus 0 is the clear winner. So we are going to report 30 back to the calling function, which is trying to figure out the answer for when there are 4 stones. So here again, what we're going to ask ourselves is, where did you come from? Did you come from the third stone or the second one? If you came in from the third stone, then the cost of that jump would have been 50, and the total cost would be 50 plus 30, which is 80. Versus if you came in from the second stone, then the cost of that final jump would be 0, and that gets tagged on to 20. So 0 plus 20 is 20. So clearly the better of the 2 options here between 80 versus 20 is 20. So we are going to record that as our final answer at this stage. Now let's go back to what's going on when we land up at the 5th stone. This is what we are trying to understand now that we've understood everything up to the 4th one. So how could you have come to stone number 5? You could either come in from the 4th which would have involved a cost of 50 plus 20 to get to the fourth stone itself. So that's 50 plus 20, 70, versus you could have come in from the third stone, and the cost of that jump would be 0, and the overall cost would be 30 plus 0, which is 30. So you can see that 30 wins this round, and that's what we're going to keep track of as we move on to the final stone, and this is going to be our final answer. How did we land up at the final stone? Did we come from 5, in which case the last jump would have cost us 10 and the total cost would be 30 plus 10, 40, or did we come from stone number 4, where the cost of the final jump would already be 40, and 40 plus 20, the total cost would have been 60. So between 60 and 40, again the winner is 40, and that's what we're going to report as the final answer. And we are pretty much done here, because this is all that we have been asked to report, the final cost of an optimal solution. But on the other hand, what if the problem also asked you to actually provide a sequence of jumps whose total cost matched the optimum that you are claiming? You might have already seen, as we worked through the example, a way to do this as well. So all you would need to do is a little bit of extra bookkeeping to keep track of basically what drove your choices as you went along. So for instance, in the very last step, when we got to 40, we want to make sure we understand how we got to 40. So the reason the answer was 40 was because we came in from stone number 5 with a cost of 10. And how did we get to stone number 5? Well, we got there from stone number 3 with a cost of 0. And how did we get to stone number 3? Well, we got there from stone number 1 with a cost of 30. So if you essentially just keep track of where you came from by figuring out who won the comparison when you calculate the answer, just keep that extra piece of information. Then just like we often do by following parent pointers, you could essentially run a backtrace to figure out what choices led to this final conclusion. And of course, when you're sharing your answer, you typically want to reverse the order so that the jumps happen in the sequence that they're supposed to happen. So I think it's a fun exercise to modify the program that we have here so that it outputs one of the optimal sequences. Notice that you're going to break ties arbitrarily. So which sequence you print will depend on how you've broken ties, but no matter which sequence you print, they will all be optimal. But your tie breaking may be different from mine, so the actual sequences we print may be different. And most judges, when they ask you for a sequence that is optimal, they will accept any valid sequence. So they will typically run a check to make sure that the cost of the sequence that you have printed actually matches the optimal cost, and that's what they will care about. Sometimes, occasionally, you may have a requirement which is along the lines of print the lexicographically smallest optimal sequence. In this case, you have to fine-tune your tie breaking to prioritize the lexicographically better option at every step. So these are some details that are worth keeping in mind. I should say that this is a common feature of dynamic programming based approaches, which is that by doing just a little bit of extra work in terms of tracking the choices that you're making as you go along, you will be able to output not just the optimum value, but also an actual solution that witnesses that value. So I think this is a good thing to practice and get used to. Some people call this running a backtrace on your DP, and essentially it is something that's useful in the competitive programming context because you are often required to actually produce a solution. And just in case you're using dynamic programming based approaches for solving real world problems at work and so on, often you are interested in an actual solution, not just a value. So do keep that in mind, and let's move on to making some general remarks about how dynamic programming based approaches typically work, summing up some of what we have seen even just through this very introductory example. So you can broadly think of dynamic programming as being memoization on top of recursion. So you come up with a recursive approach to solving your problem and you make it efficient by memoizing it like we did. I'd say that usually the memoization part, at least in terms of implementation, is usually routine. You just have to figure out how to allocate space to the answers that you're interested in and make sure that you just modify your recursive subroutine so that there is that initial check for whether we really need to do this or not. Okay, but what enables you to do memoization is coming up with a recursive algorithm that has enough redundancy built into it so that the memoization is eventually useful. So usually the heart of the problem is in coming up with a recursive approach to solving the problem that's appropriate for memoization going forward. So to come up with a recursive solution, well, again, there is no formula and every problem is going to be different, but typically the mindset with which you want to think about recursive patterns is to see how best you can break up your problem into natural subproblems. And again, as you practice more and more problems, you will begin to get a sense of how people typically chop up problems into smaller pieces. Sometimes for array or sequence-based problems, you are either looking to chop things off from the end or the beginning or even some subsection in the middle. Sometimes your pieces may have to be subsets of some collection of elements. If you're working with graphs, say for instance you're working with a tree, then natural subproblems are typically subtrees that you obtain when you delete some root vertex. So you try to figure out the answer at all of these subtrees and then somehow see if you can piece them together. So normally when you're doing recursion with the hope of memoizing going forward, you want your recursive subinstances to actually have enough overlap so that you can leverage that overlap to save yourself time. You also want the pieces to be useful in the sense that you want your answer to be in some way a function of the pieces that you develop. Like we did for the frog problem, the two pieces that we solved were directly helpful in finding our final answer. And we also had substantial overlap, as we just saw, and that helped us eliminate a lot of the exponential part of the search space. This is one of the reasons why some people think of dynamic programming as being essentially clever brute force, because when you first write down your recursive approach, it's practically a brute force approach. It's exhaustive and its correctness is easy to prove because it's exhaustive. But then after that, you take a closer look and you identify all of this redundancy and you memorize, and that's going to save you a whole lot of time. So this process of doing dynamic programming is usually called top-down dynamic programming, which is essentially you start by solving the problem at the top. That's the original problem. So you start off by invoking solve of n or something like this. And this is essentially recursion, but we save the day with the modification that allows us to save time by using space, essentially. So when you write your dynamic programming solutions in this style, one advantage is that you're essentially building off of the recursive paradigm in a small way. So it's really your recursive code with some small but important tweaks. So if you're somebody who is already used to writing recursive programs, then there's not much additional work to do to elevate it to the status of being an efficient dynamic programming based solution. Also, the other nice thing is that you only compute what you need based on the recursive calls that actually happen. You'll probably appreciate this more when you see the contrast with the bottom-up approach, which is something that we're going to discuss next. And I think one of the reasons it's worth knowing a different way of really implementing the same thing is because the other style, which is the bottom-up style, is sometimes cleaner from the point of view of memory optimizations. So if you wanted to save some space, then it's sometimes easier to do when you visualize this whole thing as a table that you're filling out, as opposed to this stack of recursive calls that are being made and that are doing their thing. They're really doing the same thing behind the scenes. It's just a different way of implementing the same idea. So we're going to continue this conversation in the next module, where we look at a different problem and we're going to implement it using the so-called bottom-up approach. And I would suggest suggest that for both problems, you do the implementation in the other style, the one that has not been given, just to get some practice. I think it's a good idea to be flexible about which style you use, because in certain situations, one may have a small advantage over the other, although it is true that most people have sort of their preferred default styles when it comes to dynamic programming, and they would only switch if there was a specific need to switch from the point of view of a certain kind of optimization and so on. So as I just said before, I think it's a good idea to at least be aware of both the styles and be reasonably comfortable implementing a given solution in either of these styles, because that may be something that's useful in a specific situation. Having said that, in the early stages, most elementary dynamic programming based problems are such that this choice shouldn't really matter. So if you find one style much more intuitive or natural than the other one, it's perfectly fine to just stick to that for now. Let's continue this conversation in the next module, where we will use another introductory example to exemplify the style of bottom-up dynamic programming.